Let's talk now about related rates. As soon as you see this word here, rate or rates, what you want to think is derivative. After all, rates or rates of change are derivatives. And just like the title says, related rates, what we're going to talk about here are related derivatives. We're going to take one derivative, relate it to another. Before we go any further, let's be sure we know what a rate is. We're talking about related rates, so we need to know what we mean by a rate. So a rate, that's a ratio in which the numerator and denominator have different units. Here's an example. We might have something like 30 miles per hour, right? MPH. Per is that line right there. So this is a ratio, but it's a specific kind of ratio. It's a ratio in which the numerator and the denominator have different units. Now, if the numerator and denominator have the same unit, like if I wrote like this, 30 miles to 20 miles, we have the same unit here. This is just called a ratio. All right, so this is just a ratio. So a rate is a particular type of ratio, a ratio in which the numerator and the denominator have different units. And we are talking about related rates. So we're talking things like miles per hour. Let's look at an example now. And I'm going to work this example all the way through in detail so we see exactly what's going on. There's going to be probably more discussion here than if I was just trying to solve the problem myself. But let's see what's going on in detail. So here's a problem. We have a sphere, and we know that the radius of the sphere is increasing, so the radius is getting bigger at the rate, I see the word rate, I think derivative. And sure enough, here's a rate, 3 feet per hour, right? Different units. So I've got a sphere, and the radius is getting bigger at the rate of 3 feet per hour. So every hour, this radius has increased by 3 feet. Now here's what we want to do. We want to find the rate, all right, find another derivative, find the rate at which the sphere's volume is changing when the radius of the sphere is at 7 feet. All right, so we've got two rates here. We've got the radius increasing at 3 feet per hour, and we want to find how is the volume changing exactly at the point when the radius is 7 feet. So first up, whenever we can, let's draw a picture. Now we can draw a picture in this case because it's a sphere. So I'm going to draw a picture because what I'm trying to do is establish a relationship between the radius of a sphere and the volume of the sphere, and then their derivatives. So I'm going to draw a picture. Now, pictures help us to make relationships more visual. So if I draw the picture, I've got a better chance of getting the relationship, and they promote better access to the equations. So let's get a picture here. So we've got a sphere. I'll draw it up here at the top. I'll draw a circle, and then I'll put kind of an equator line to make it look 3D. And now that I've got my picture, what I'm going to do is this. I'm going to identify all variable quantities. So anything in this sphere that can vary, I'm going to label. All right, now I know that the radius is increasing, so I'll put a center here and draw an arrow out to the circumference, and I'll label that with an R for radius. So I've identified one variable quantity, that's the radius. Now there's another variable quantity, right? If you look down here on the left here, the volume is changing, so the volume is variable. So I'm going to label this, I think I'll just put it right here for volume. All right, so I've identified my variable quantities. Now down here at the end of this sentence, it says the radius is 7 feet. Now that's not variable, so I'm not going to identify that anywhere here. This is 7 feet, that's a constant. I'll use that at the very end. Now the next thing I'm going to do here is I'm going to try to establish a relationship between these variable quantities. Now this is a sphere, and there's a well-known relationship between the radius of a sphere and the volume of the sphere, so I'm going to write that here. It is that the volume is equal to 4/3 pi r cubed. And now before we just start going on, let's get a big picture of what we're doing here. I've got two variables, radius and volume of a sphere. So I've got the radius and I've got the volume. And what I've established here is a relationship between these two right here. So the relationship, this can either be known, right? The relationship can be known, or it can be established. Now we happen to know this one because this is just the first example. So I'm just going to write the relationship. It's known. Now if you don't know it, you may have to work a little bit to establish it. And we'll do that in a following example. So what we've done so far is we've drawn our picture. We've identified all variable quantities, right? The radius and the volume, because they're changing. And we have established a relationship between the quantities. So we were lucky here in the first problem. We're just using a very well-known relationship. Now the next thing that I want to do is I'm going to differentiate. So I'm going to differentiate, now I'm going to be over here in the picture here. I'm going to differentiate both sides of this equation right here. My relationship, I'm going to differentiate through this relationship, and I'm going to do that to get how each quantity changes. So I'm going to differentiate here to get how the volume changes. I'll differentiate here to get how the radius changes. And when I differentiate, now look what we've got here. When I differentiate, the volume, well, this is a function of time, right? Because look back over here. What rate are we given? Per hour. So things are changing relative to hours, relative to time. So I'm going to have to differentiate V with respect to time and then R with respect to time. So this is implicit differentiation, right? I'm not finding dV dr. I'm finding dV dt and dr dt. So I'm going to use implicit differentiation. And if you don't remember implicit differentiation too well, I'll do it carefully in this example. So here's the plan. I'm going to go over here and I am going to differentiate. I'm going to differentiate in order to get this. So what I want down here is the rate of change of R with respect to time. And then I'm going to do the same over here. I'll abbreviate a little bit here. I'm going to differentiate to get, okay, so I differentiate, and now what I want here is I'm going to get the rate of change of V. So we'll do this, but notice what we have here then. I started with this relationship between R and V. I differentiate both sides, both variables, and that gives me the rate of change of each. Now what I've got is this. I can relate these two, and that's what I'm trying to get. Look back to the original problem. We know that the radius is increasing at 3 feet per hour. So this one is known. And what I'm trying to get is this one. So I've got a relationship now. So I should be able to get that if I can differentiate it. So here's our relationship. V equals 4/3 pi r cubed, right? V equals 4/3 pi r cubed. Now I'm going to differentiate, but with respect to t. So in order to do this, I'm going to have to use implicit differentiation. Now I'm going to show the implicit differentiation very carefully in this one, in case you may not remember it. If you do remember how to differentiate implicitly, you can just fast forward a bit. But here's what we're going to have. I'm going to have V. Now V is really a function of t, because as time changes, the volume changes. So this is equal to 4/3 pi r cubed. But r, well, r is a function of t. So I'm going to write this. R is a function of t cubed. All right, so what I've got here is that V equals 4/3 pi r cubed, but I'm writing it more directly as that V, the volume depends on time, and the radius depends on time. Now let's differentiate. So instead of writing v prime, okay, I could write this, v prime, but then it's not clear if the prime means with respect to r or with respect to t. So I'm going to write dv dt, right? That is how the volume changes as time changes. So dv dt is equal to, now in this derivative here, we have a constant, so I'll write that constant, 4/3 pi times, now here is the variable quantity. And look at it, it's a power. So I'm going to have to use the power rule, right? The chain rule, the power rule. So I know how to do this. I take the derivative of the outside times the derivative of the inside. So let's do it. The derivative of the outside is 3, and then r of t, and then decrease it by 1, right? That's the derivative of the outside. Bring the 3 down as a multiplier, decrease it by 1. There's the derivative of the outside. In fact, I'll even write that here. The blue doesn't work too well, so let's not do that. Let's use, I'll just use white. All right, so here's the derivative of the outside times, now the derivative of the inside. Well, the derivative of the inside is just r of t. So I'm going to write that as just dr dt. There's the derivative of the inside. So now that we've seen that implicit differentiation part, I mean this part right here, like, okay, this part right here, I'm just going to write this as this. So if I was starting this problem right from up here, I'm going to differentiate implicitly. Here's what I would get. I get dv dt equals 4/3 pi, and now let's differentiate this right up here at the top. Just differentiate this. You know what you're going to get? You're going to get the 3, because that comes down. Then you're going to get dr dt, or r, right? That's just an r squared. So we're going to get 3 times 3 r squared, and then times dr dt. So we can fix it up a little bit here, right? Here's what we can do. This 3 will cancel with that 3. They'll divide out. So that will give us dv dt equals 4 pi r squared dr dt. Well, now we're in good shape, right? Because what I've got a relationship, right, between the two derivatives. That this derivative is equal to 4 pi r squared times this derivative. So let's substitute now our constants. So if I substitute the values of the constants, what have we got here? Well, first of all, I don't know dv dt. There's nothing here, but I do know r, right? Because I want this whole thing when the radius is 7. All right, so now at the very end, I'm going to put r equals 7, and then I also know this one, dr dt. That's given up here, right? The rate of change of the radius is 3 feet per hour. So when I make the substitution, I'm going to use the units so we know what we have when we're done substituting and computing. So how about dv dt equals 4 pi times r. Now r is 7 feet squared times dr dt. Now that's given in the problem as 3 feet per hour. So let's keep going here. dv dt is going to be 4 pi times the square, 49 square feet times 3 feet per hour. And then, let's see, we'll have to multiply the 4, the 49, and the 3. So I've got, I'll do that over here. We'll get dv dt is now 4 times 49 times 3. If I did that right on my calculator, is 588. So 588 pi. Now look at the units here. I've got feet squared times feet. Feet squared times feet is feet cubed. So this is cubic feet per hour. And that 588 doesn't even look like it's readable. So let me rewrite that again. How about 588 pi cubic feet per hour. And that's the solution to our problem. Go back and read the problem here. It says the radius is increasing at 3 feet per hour. Find the rate at which the sphere's volume is changing. Now the sphere's volume is changing, that's dv dt, and I found that rate. It is at, when the radius is 7 feet, it's changing at 588 pi cubic feet per hour. Now cubic feet, that's a volume, right? So our units match. Now it's a rate because it's cubic feet per hour, different units. Now we could, I guess, put in 3.14 to get an approximation, but we're good. Let's just claim that that is our solution. Now, what is it doing? Well, look, 588 is positive, pi is positive, so this is positive. So what do we have? dv dt is positive times positive is positive. Positive, which means that v is increasing. I think it's important to do one more thing. We've got a number, 588 pi cubic feet per hour, but it's nice not just to get a number, but it's nice to be able to tell somebody what it means. Let's interpret this value. Now, to make that interpretation, I'm going to write our number like this. dv dt is equal to, now, I've got a numerator and a denominator. So I'm going to write this whole thing as a fraction. So I'm going to write it like this. 588 pi cubic feet over, now it's not just an hour, it's 1 hour. Right? So what it says is that as t changes, as t increases by 1, v will increase by 588 pi cubic feet. So here's our interpretation. In the next hour, in the next 1 hour, right, the next 1 hour, from hour 7 to hour 8, right? Remember, we started this at r equals 7. So in the next 1 hour, from hour 7 to hour 8, the volume of this sphere can be expected to increase by about 588 pi cubic feet.